Hi folks, and welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to calculate electric fields. I'm going to make this kind of a conceptual example without any numbers. So what we're looking at here is we've got a pair of point charges, a negative charge here, a negative charge here. We're going to say that this guy's got a charge minus Q and this guy plus Q. So in this video we're going to assume these are both the same charges, and again they don't have to be in general, but I'm going to just to make it a little bit shorter. Right, and we're going to imagine this horizontal distance here is x, and then these are separated by a distance y. And what we're going to do is, picking a point right here, we're going to try to calculate an expression for the electric field vector at this point. Now, there's nothing special about that point. Again, I could pick any point on this page or even in 3 dimensions to find an electric field vector. This is just a nice point. It'll be a nice point with some symmetry, and it'll make it a relatively easy calculation. So the first thing we need to do is draw electric field vectors. So I'm going to go ahead and draw the electric field vectors at this point due to these two charges. I'm going to take this guy first. So the electric field direction, remember, is the direction is the force direction on a small positive test charge. So we imagine putting a proton right here. If we put a proton here, these two charges will repel. Force direction on the proton will be up and right. Therefore, the electric field vector is going to point up and right. And I'm going to call that an E2 because that's the electric field vector created by charge 2. Now, before I move on and even deal with charge 1, I'm going to go ahead and write out an expression for this electric field. So remember, the electric field is equal to kq over r squared, where r is the distance from the charge to the point. So this is going to equal kq over, now what I need now is this distance squared. Now, this triangle, if I look at this triangle right there, right, this leg is what I'm calling x, this leg is what I'm calling y. So the hypotenuse squared is going to equal x squared plus y squared. So I'm going to go ahead and just put x squared plus y squared for the distance squared. Now I should also put this angle in here. It doesn't really matter what angle I choose. I'll go ahead and put an angle right here, theta, and I'll deal with that later. Right now, next we're going to draw an electric field vector at this point due to this charge. So we imagine putting a small positive test charge here. This charge will attract it. Therefore, the force direction will be left, and therefore the electric field vector here due to this charge is to the left. And I'm going to call that E1. Now you'll notice that I drew this vector a little longer than this one, and that was deliberately because this distance x is shorter than this distance and they're the same charges. So I know that this electric field should be a little bit larger in magnitude. Right now I'm going to write out an expression for it. Electric field vectors have a magnitude of kq over distance squared. In this case the distance is what I'm calling x, so kq over x squared. So I've got the electric field vectors drawn. I also have expressions for their magnitudes. All right, now we've got to talk about how to add them. So electric field vectors add like any other vector quantities. I'm going to go ahead and use the method of components. All right, so this E2 here needs to be broken into components. I'm going to draw those in red. So this E2, I can think of it as an E2x and an E2, and an E2y. Good enough. Okay. So E2y, you'll notice, is opposite theta. So it's going to equal E2 times the sine of the angle theta. I'm just going to put that sine theta there. E2x here is adjacent to theta, so it's going to equal E2 cosine theta. And again, I'll deal with my sines and cosines in a minute. All right, so now when we add vectors, the net electric field vector, and what I'm going to do is I'm just going to write it out in unit vector form, is equal to something I plus something j If you haven't, if you're not familiar with the unit vectors I and j, I would go back and review. I know I've got a video somewhere on unit vectors. And this represents the x component of the net electric field vector, and this represents the y component of the net electric field vector. The x component we get by summing this and this. I said sum, but what I mean by that is vector sum. I'm going to go back and talk about that cosine theta now for a moment. If we take a look at this triangle right here, this angle theta and this angle theta are the same. The hypotenuse of this triangle is the square root of x squared plus y squared. So cosine theta is equal to x over square root x squared plus y squared, and sine theta is equal to y over square root x squared plus y squared. So I think I'll just leave that there and write these out. All right, so the net electric field vector we get by adding this and this vectorially, so that's going to equal E2. I have a feeling I'm going to need more room, so I think what I'll do here is before I start writing, I'm going to clear that. Start over to the left. All right, so the net electric field vector is going to equal this, E2 cosine theta, which is going to equal kq over x squared plus y squared. And then the cosine theta, again, I can get from this triangle. Remember, this is theta, so cosine theta is going to equal x over square root x squared plus y squared. So that's this term. And it's to the right, and I'm doing right positive for this sum. Right? Minus this expression, minus kq over x squared. So this represents the x component of the electric field. I'll just put an I on it. Pretty sure that's going to end up being a negative number. Oops. I'm pretty sure that this term, vectorially is larger than this one, so this will be a negative number, which means to the left. All right, now, the next term is going to be for the y component of the net electric field vector. Now, this guy doesn't even have a y component, so it's no problem. So really, all we're going to have is this, which is E2 sine theta. And here's how E2 is calculated. So that's going to equal kq over x squared plus y squared. Again, that's the magnitude of E2. And then times sine theta. And again, here's theta, which is the same as this. And sine theta is equal to opposite over hypotenuse. So I'm just going to multiply that by y over square root x squared plus y squared. And that's in the j direction. So, again, this video is just intended on showing, 1, how to draw the electric field vectors, 2, how to break them into components where appropriate, 3, how to add the electric field vectors, how to add the electric field vector components, which is what I've done here and here. Presumably, if we had numbers, we could go through here and get values, but again, this is meant to be kind of a conceptual video, so I think I'll just stop it right there. Have a great day.